My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 566. In this lecture, we will try to understand optimizer's hill descent. Recall our previous lectures. We discussed about gradient descent, why gradient descent is useful in finding maxima minima. We discussed about stochastic gradient descent, mini batch based gradient descents, how these are useful for finding maxima and minima. Yes, that's just go through my previous lecture series. I explained all these concepts in detailed manners. Now let me consider a function L, minimize a function L, loss, let's say it's a function, what is W here? W is weight. You have a loss function of weights. L of W means loss function of weights. We want to find the best W that minimizes this loss function, isn't it? W star equal to argmin of W. L of W means we want to find the best W that minimizes this loss function L of W. So, whenever you want to solve optimization problem, SGD and variations of SGD works very well. But in the case of deep learning, the simple SGD or even batch SGD or mini batch SGD cannot solve all the problems very well. We will see why, what problems it has. But before we understand other variations of SGD or more recent advances, and remember, most of these advances have happened last 10 years. These are advances on SGD primarily for deep learning. We learn a bunch of these algorithms and how they work. But before we go and understand these algorithms, I want to give a graphical understanding of what optimization all about with a nice analogy or comparison to descent degree. Of course, we discussed all these things in my previous lectures. Just anyway, let me recall it once. Suppose let me draw same diagram here and explain this. What is our task? Our task is to what is our task? Our task is to minimize, isn't it? Minimize a function L. This function, what is this function? This function is L. L is a function of weights. Parameters are weights, just like deep learning, just like multi-layer perceptron. Even in logistic regression, we are trying to find weights, isn't it? That's the problem we are effectively solving. That's the problem we solved, isn't it? Imagine, let's assume W is a scalar. Yes, just for simplicity, W, let me say this is first case here. W is a scalar, means it is just one value. When I can plot L of W, just see, this is my L of W is on y-axis. If W is on x, if W is just a scalar or it has one dimension. What is scalar means? Basically, it means it is just one dimension, isn't it? It is just one variable. I can plot. I can plot my what is this? I can plot this L of W, isn't it? My loss is on y-axis, isn't it? There are many ways this loss can look like. One way the loss look like is let me say this is loss looks like this. These are squared loss, which looks like this. Just try to recall our squared loss. This is just like squared loss. This is like a parabola. So this is my L of W, isn't it? What is my L of W here? This is my L of W, isn't it? It is just like squared loss, isn't it? Here you have one minima. Is it right? We discussed all these things. One minima here, you have minimum value. It occurs at origin at 0. This is called the minimum. This function has no maxima, isn't it? It has no maxima. we talked about maxima and minima in a lot of detail in our optimization chapter, isn't it, where we define what is minima, what is maxima, isn't it, and stuff like this. Just I am recalling all those concepts, isn't it? This function has no maxima because as w increases, why it has no maxima? As w increases, just see, as w increases, your this function keep on increasing, isn't it? If your L of w is keep on increasing, f of w keep increasing, so that maxima is infinity. Minima happens at w equal 0. So it has a minima and it has only one minima. Now let's take another example. Let's take a slightly different example, isn't it? Just let me consider this example. Imagine my w is here, my w is on x-axis, isn't it? If my my L of w is on y-axis, let's say it look like this. Let's assume it look like this. Let's assume this is your L on y-axis. You have L of w, isn't it? Let's just say now here. What is minima? Because here this is minima because all the points that are which, let me say this is a minima. At this point, let me say this is a minima. Yes. Why? Because what's the reason? This is a minima because all the points that are surrounded to, you see, all the points that are surrounded to this corresponding to w1, yes, corresponding to w1, you have the minima. You are calling it as a minima because you are compared this with the points close to this. This point is also minima. There is also point corresponding to w2, isn't it? This is also minima corresponding to w2. It is also minima corresponding. There is another minima corresponding to w3 is also minima. You have three minimas here, but among these three minimas, your w3 corresponding minima w3 is the lowest among three. So this is among these three minimas, a minima which corresponding to w3 is the lowest one. So this is called global minima because it has the lowest value as compared to all minima, isn't it? W1 minima corresponding to W1 is called local minima because this value is minima compared to this value is minimum compared to this particular locality. But minima corresponding to W3 is the minimum compared to all other values in the function. Therefore, that minima corresponding to W3 is called global minima. Actually, we already discussed all these things. This is called minima which is corresponding to W3 is called global minima, isn't it? Minima corresponding to W1 and W2 are called local minimas. At minima, you always has slope or gradient is equal to 0. This also we discussed long back. At minima or maxima, your slope or gradient is equal to 0. We saw this in optimization chapter. At both minima and maxima, you have your gradient or derivative of loss function with respect to w is equal to 0, isn't it? For example, this is maxima. Just see, this is you have here maxima, isn't it? You have maxima here, you have maxima here, isn't it? I can say these are local maximas. This maxima and this maxima, what are those? Those are local maximas. Here the tangent is, if you observe carefully, here the tangent is parallel to x-axis, or I can say here w-axis. How does the tangent looks like? Your tangent looks like this. It is parallel to x-axis. To understand, tangent means your slope equal to 0 or not. You basically draw a tangent. Look at the slope. This that's what we learn in optimization chapter. Here the same thing here also. The same interpretation at maxima and minima. Your slope equal to 0. Just go to this particular site mathsfun.com. Suppose instead of x-axis I'm taking this is w, and my loss function, let me say this is L of w, function of w, isn't it? Let's say this is your local maximum, because why it is, just see, this is your local maxima. Just see here in local maxima, what is this? This is local maxima. Just see this one, isn't it? This is your local maxima, because maxima can occur at many places, isn't it? That's why I'm calling it as local maxima, as your maxima can occur at many places. Tangent parallel to w, just if you draw tangent, what is your tangent here? This tangent is parallel to w axis, hence this is the local, you have local minima. Just see, this one is your local minima, you have local maxima, isn't it? Just same stuff. Yes, so at minima and maxima, your slope of your loss function with respect to w is equal to 0, isn't it? Whether there is other type of point called saddle point. Yes, what is this saddle point? Also, we also discussed what is saddle point in our previous lectures. If you take this point saddle point, isn't it? And if you take tangent at this point, tangent at saddle point, just see, at maxima and minima, dl by loss, derivative of loss with respect to w is 0. Yes, at saddle point, if you take, even if you take a saddle point and if you take tangent at saddle point, it is parallel to w axis. So even at saddle point also, your derivative with respect to w is also equal to 0. That is, derivative of L with respect to with respect to w is equal to 0. Its derivative with respect to w is 0 for maxima minima. Not only for maxima minima, it is equal to 0 for saddle point. So the derivative equals to 0 could imply the derivative equal to 0 could imply that you are at minima or maxima, or it could be at saddle point. All three are possible. There are three possibilities. Very interesting, right? So if you recall our SGD stuff like that, we always said that we will keep updating that our updating function w nu equal to w old minus eta into dou L by dou w. We keep updating this. We keep running this in a loop where we keep updating the old value to new value, isn't it? We keep updating this old value to new value. We stop updating till this derivative dou L by dou w equal to 0, isn't it? We just try to recall. We stop updating till this derivative becomes 0, that is dou L by dou w becomes 0, and that derivative could become 0 at a minima, at a maxima, or even at a saddle point. The derivative could become 0. This point is important, at minima, at maxima, or even at saddle point. So sometimes your SGD, your simple SGD or batch SGD could get stuck at saddle point, because what happens at saddle point, saddle point, this derivative becomes 0, isn't it? Which means there is no change, and there is no change in between w new and w old, and when it does not change, you say I converged. But instead of converging to a local minima or local maxima, you could have converged to a saddle point. Then what do you do? Yes, this is the biggest problem. Then what do you do? There are ways to get rid of this. I will discuss those ways in my next lecture, that is lecture number 567. Thank you very much.